But in some very special way, you are able to probe all of these configurations. Right? So what are these good quantum computers good for? It's not a free lunch. It's not like having 8 3-bit computers. For some problems, it is. For some very specific problems, it does appear to be. But in general, it's not what it is. What they're good for is for finding global patterns, global properties, or what I sometimes call seeing the forest without actually observing the trees. I don't mean coarse-grained view of the trees. I mean you have very precise properties of the forest, but you don't know about anything about any of the trees. How can you do that? Well, quantum mechanics allows that. So what do I mean by global property anyway? But here's a math problem. Here's a sequence: 34, 12, 54, 38, 57, 34, 12, 54, 38, 57, 34, 12. It repeats. Every 5 numbers, it starts all over again. Now, the first 5 numbers are distinct. Like within the period, it's distinct, but then it repeats. That's a well-defined math problem. What's the period of this sequence? Let's make it a little harder. Let's suppose a sequence of numbers, so these are 128-bit numbers. So 16 bytes, binary, whatever the physical encoding is, we don't care. So the number 1, this would also be encoded in binary on a computer, gets mapped to this pattern. The number 2 gets mapped to some other completely different pattern. The number 3 gets mapped to some other completely different pattern, and so on and so on and so on. 729 trillion, 672 million, 729 billion, 672 million, 482,463 gets mapped to yet another distinct pattern. And then 729 billion, et cetera, and 64 gets mapped to, right? I know I can see it. You've noticed that's exactly the same pattern that 1 got mapped to. And then that's the cycle, right? This is the same as what 2 got mapped to, and so on. So I'm guessing, I'm getting the sense that you profoundly don't care about what those precise patterns were. Right? But if I wanted to classically, on a classical computer, find that period, the naive way is just to do 700 and whatever billion different calculations. You collect all this garbage data you couldn't possibly care about until you see a pattern. It takes up a lot of memory. There's actually more clever algorithms that take square root of that many steps, roughly 1 million calculations, and they'll see a collision, they'll see the same pattern. It's like the birthday surprise paradox. If you take about 20-some people in this room, there's high probability that they have the same birthday. 2 people have the same birthday. So there's a square root, well-known square root method in computer science and cryptography. So, but that's still a lot of garbage information you don't care about. You just want to know the period. What a quantum computer allows you to do is, you take the 128 bits for the answer. You take about 100 bits or so to encode 1, 2, the n, the number n. You compute the nth pattern. But you do it, you prepare a prepare a combination of all the input numbers, which is an easy thing to do. You have, say, 100 quantum bits. You just make each of them into one of that square root 0 plus square root 1 state. So it's really easy. You just quantumly flip each bit. Those input bits, the bits that encode, the 2 and the 1 and then so on, it's very easy to prepare them in a combination of all the possible patterns with a small number of steps. Then you compute the bit pattern. You just do that one computation on this barely, roughly 200 bits. And what you physically embody is, 1, the first pattern, 2, the second pattern, 3, the third pattern, n, et cetera, n, the nth pattern. In those small numbers, in just that one quantum computer. It's somehow in all of those states at the same time, whatever that means. Now don't look at it. If you look at it, all it does is it effectively collapses to one of those states, and all you get is some random input n and the nth pattern, which you don't need a quantum computer to do. You just randomly pick an n and compute the nth pattern in that case. Don't look at it. What you do is you kind of jiggle it and see how it jiggles back. And you do what we call a quantum Fourier transform, which is very much like the Fourier transform if you're an engineer or you're into signal processing and so on. They're very useful for finding patterns and periodicities in signals. So you do actually have what Peter Shor discovered is a very simple sequence of pulses on these bits, these quantum bits. First, this Fourier transform type thing. It's essentially the equivalent of when we went, instead of looking at them, don't look at that photon this way, look at it this way. That's the 1-bit version. The 128 or 100-bit version is called the quantum Fourier transform. But you're looking at it in a different way. Then what you see is a number which encodes the inverse of the period. Actually, an integer multiple of the inverse period. So you'll either see something that's an approximation of 1 over this large number, or 27 over this large number, some integer over this number. And if you have a good enough approximation of a fraction, there's a well-known method in number theory called the continued fractions algorithm that spits out the fraction. It cleans up the noise. With a denominator, you pick a denominator size. It'll give you a sequence of fractions that approximate that number, and ultimately you will find that denominator with high probability. So it'll spit out essentially the period. And you only need one. You could do that. If you do this once, you have a good chance of finding it. If you do it 2 or 3 times, your chances get really close to 1. So with a very small number of steps, you don't have to do 729 billion or square root of 729 billion steps. Just do 1 or 2 or 3 quantum glimpses at this data, and it will spit out the period. But if somebody asks you what was the 3rd or the 4th or the 5th pattern, you'll have no clue, because you didn't look at it. You couldn't have looked at it. So you get this global property, but you don't learn any of the details. Now I'm sensing that nobody in the room really cares about finding the period of large sequences. Not quite nobody. I see at least one famous cryptographer, Ron Mullen here in the second row, who understands very well what the implications of an efficient period finding algorithm is, and I'll tell you a bit more about that later. But for most people, it's not that interesting. I'm demonstrating this. This is not so much an interesting, application, but I'm trying to get a sense of what I mean by a global pattern. The applications that would be interesting to most people include simulating quantum materials. Right? The kinds of materials that our colleague, Duncan Haldane at Princeton, who's a distinguished visiting research chair here at Perimeter, that he just won the Nobel Prize for on Monday, along with his 2 other colleagues. They're studying these quantum materials, which have offer these new phases of matter, basically. Phase of matter, you have gases and liquids and solids. But quantum mechanics at low temperatures offers entirely new phases of matter that don't depend on temperature, but some other parameters. And if you want to study these materials, it's really, really hard, because you have to study them in a quantum mechanical way. You have to look at how all these configurations, when you want to say what's the probability that after a certain amount of time you end up with this configuration, or this is just an this is an arbitrary, fictitious thing, but that you get a 1 here, that you get a certain pattern. You have to explore all the ways to get that result, add up the amplitudes, pluses and minuses, and so on. It's a really hard calculation. Quantum computer can help with some of these questions about quantum materials. Or if you want to study a chemical reaction at the quantum mechanical level, a quantum computer can help. Another example for how a quantum computer can help is searching and optimizing so-called needle in a haystack problems. So in optimization, and I see famous optimizers in the audience too. You know, we're not literally looking for a needle in a haystack. This is a metaphor for there's a solution to a math problem, something very important. You're trying to optimally allocate a resource. You're trying to design a building to be earthquake-proof. You have money for so many dampers. How should you configure those dampers to maximally protect you against earthquakes? You can try tons. There's countless, exponentially many configurations. Given a configuration, there's models to test how earthquake-proof it is, but you don't have time to go through all of them. So these are the kinds of questions we look for that optimizers in industry try to solve. Or there's other problems where, if I give you the answer, you can check it, but good luck trying to find it. If there's no structure, the best thing we can often do is just try all the possibilities until you hopefully find that answer. So these, all these pieces of hay or this, blue needle that I'm not looking for represent are the wrong answers or the non-optimal answers. And this needle is the optimal answer that I'm really looking for. Let's suppose there's just a million possible answers. Usually there's many, many more, but let's say a million. An obvious thing to do is just randomly guess a solution. And you're probably not going to find it. And try again and again and again about a million times, and then you'll probably find that needle. But remember, if you quantumly just guess a random solution, a random place, a random configuration of a million possible configurations, a million possible ways you can, if you're trying to do airline scheduling or scheduling classes at a university, you look at all those configurations, pick one at random, right? But quantumly pick one at random. Have your quantum computer prepare them all at the same time. Again, don't look at it, because if you look at it, you're just going to collapse to a random guess. Remember, quantumly, what's going on underneath is these all exist with amplitude square root of 1 in a million, which is 1 in 1,000, 1 over 1,000, plus or minus. So this idea that Lov Grover at AT&T Bell Labs came up with was essentially saying, don't look. Make a quantum guess, but don't look at it. You got the answer with amplitude 1 in 1,000. Then make another quantum guess, but don't look at it either. And another one and another one and another one. If you do it, and this is not an easy algorithm to design, but effectively what he came up with was a way, with about 1,000 quantum guesses, without looking at them, he boosted this amplitude to be close to 1, either 1 or minus 1. And then you look at it. Because by then you've boosted that amplitude to be close to 1, and 1 squared is 1, right? Or minus squared is 1. And you solve that optimization problem with just 1,000 looks instead of a million looks. Or if it's a 1 in a trillion problem, you only need about 1 million looks instead of 1 trillion looks. So there's a host of there's a host of application areas for quantum searching and optimization that take advantage of what's going on under the hood in quantum mechanics, and these quantum features that I've told you a bit about. There's another interesting feature of quantum mechanics known as, which I'm describing as eavesdropper detection. It's related to the Heisenberg uncertainty principle. So earlier, I told you I could send light to you in one of 4 possible states. Can you perfectly distinguish all 4 of those states? If I don't tell you which of those 4 I'm choosing, you can try. If you put your filter up this way, you'll be able to tell, you can perfectly distinguish, say, horizontal and vertical, but you'll totally randomize the diagonal. If you put it diagonally, you'll be able to perfectly guess the diagonals, but you'll totally randomize the horizontals and verticals. And you can try everything in between. There's always something that you're going to you can either mess up 2 things a lot and a couple things not at all, but you'll mess up everything. Or you'll mess up everything a little bit. There's a minimum amount of disturbance, no matter how you slice it. So if I send one of these 4, if Alice, who's trying to establish a secret random string with Bob, she sends one of those 4 states through an optical fiber, now when Bob guesses if he guesses, whether horizontal vertical correctly, he can perfectly and she sent something that was horizontal or vertical, they can cleanly communicate a bit. And if he correctly guesses plus or minus 45 degree basis, as we call it, and that's what she sent, they can perfectly communicate a bit. And in the case that they were mismatched, well, they can just discard that data. So if there's no eavesdropper, Alice and Bob can get some perfectly correlated bits. But if there's an eavesdropper, she will necessarily disturb some of those bits substantially. And that disturbance will be detectable by Alice and Bob. Because there'll be an instance where Alice sent a horizontal photon, Bob measured in the vertical horizontal basis, but didn't get the right answer. So they know there was something going on there. And statistically, you can have a very strong estimate of how much Eve has interfered. So she cannot interfere without detection, interfere significantly without detection. So this gives Alice and Bob a way to share secret bits. Now most people don't care about secret bits. However, if you're doing cryptography, that's very useful. The secret bits can be put into encryption algorithms to encrypt your information. So if I want to communicate securely, I don't take my message, my valuable secret message, and send it along the optical fiber and have the consolation prize of knowing that it's been hacked. No, I don't do that. I keep it, I send random garbage data through that fiber. I test if it's been spied on. If it hasn't, well then it was private data now. Generic private data. And then I use that secret key to encrypt the data and transmit it securely through an untrusted medium. And quantum cryptography has been developed in numerous technologies over the past decade or more. Switzerland and these other two are from China. And there's others. I just didn't have room for all of them. There's one of the other first prototypes is from the United States. And these point-to-point quantum cryptography links have been leveraged into trusted repeater networks. So in the United States, in the Ohio area, they're working on, these would be trusted nodes. Right? Same here in Japan, Switzerland, in China. This is like a 2,000 kilometer chain with a few dozen trusted nodes. So you might say, I don't really want to trust the node. Well, it's a heck of a lot better than having to trust the whole fiber along the way, right? So you can leverage point-to-point quantum key establishment, or what people call quantum key distribution. It's discoverers Gilles Brassard and Charlie Bennett called it. Now, when quantum technology matures to something not quite as sophisticated as a full-fledged quantum computer, but something in between, into something called a quantum repeater, we don't actually have to trust these intermediate nodes. You can have a purely untrusted infrastructure, and you just verify yourself whether anybody's been tampering with your data. And you establish a key. For now, we have to trust these nodes because we don't have quantum repeaters, and we can't send photons through fiber more than 100 kilometers or maybe 200 kilometers or so. Another strategy for long-distance quantum communication is free space. So there's two natural media for photons. One is through an optical fiber, another is just send it through the air. I mean, there's photons going through the air right now. And they actually can go through relatively unencumbered. And my colleague Thomas Jennewein, just a few days ago, he's been building his satellite QKD receiver for a number of years now, preparing it and testing it for actually be launched on a low orbit satellite. But just a few days ago he tested it on an airplane around Smiths Falls in Ontario, Canada. And it worked just fine. And so quantum space science, I first heard of it in the 90s, late 90s, by our colleagues at Los Alamos National Labs. And then a number of colleagues in Europe, including Thomas, started driving a quantum space science initiative in Europe many years ago. And then we recruited Thomas to Waterloo, and he's been driving the Canadian quantum space science program. A big milestone in this field recently, this summer was China launched the first quantum communications satellite into orbit, which will enable a number of quantum space science experiments, including long-distance quantum cryptography. There's other potential applications of quantum technologies, such as quantum money. This unlike quantum cryptography, QKD, quantum key distribution, which is available with today's technology, quantum money will require a full-fledged quantum computer and stable quantum memory, so not available in the short term. But the idea is very interesting and profound. Digital money is hard to realize. You can't really realize it in practice with classical systems. Or at least digital money that well reflects today's classical paper money. Money that can be checked offline without any interaction, without some blockchain, right? Without interaction with a trusted third party. Quantum mechanics could enable that. Because you can't copy quantum states. If you could copy them, you could disturb that. You could measure them without disturbance. Right? You just copy it. You trash the copy, but you have the original, right? So you can't copy quantum states. So quantum mechanics gives us a new form of money, say. It could be available in the long-term future. So to sum up the first part of my talk, this new quantum paradigm brings new possibilities, new very exciting positive possibilities. Designing new materials and drugs, simulating chemical reactions at the quantum level, optimization. I haven't even had a chance to talk about sensing and metrology. I mean, one of the reasons we don't have a large full-scale quantum computer yet is these devices are very sensitive, and we still have to figure out how to engineer them to bring the noise levels down to a point where we can scale them into large, reliable systems. But if you're sensitive, then maybe you're a good sensor. People are working on it at IQC and around the world on next-generation sensors for medical imaging, detecting weak electromagnetic fields, landmine detection, and so on. I've already mentioned quantum communication, and I really think we're just scratching the surface, because we don't really have the devices in our hands. There's not, at least not in the wide scale, for people to try things and figure out what the useful applications might be and how they might help us in our lives. We don't have them yet. Just like in the 40s, we certainly didn't imagine applications of computers today. Or in the 80s and 90s, the applications of the internet today were far beyond most of our imagination. Or wireless communications a century ago. Who would have thought of what we're using it for today? So I think we're just scratching the surface in terms of what the possibilities are. There is, however, one tiny catch. I mean, we're all eager to seize the wonderful applications of quantum technologies, because it will bring great value to society. Even the things we know of today, and even more when we factor in all the things to be discovered. However, it is a more powerful form of computing. So things like multiplying. So let's go to, in the classical paradigm, multiplication is easy. But if you give me, there are problems that are hard. Like if you give me a large number and ask me what are its prime factors, that takes a really long time on a classical computer. You give me a 2,000-bit number, 600 or so digit number, it's beyond current computing. You can use the best known algorithms, all the available computing power today, we can't do it. So it's hard. And it turns out a certain form of public key cryptography, a widely deployed form of public key cryptography, is based on this problem being hard. We need this to be hard for those systems, for our internet today to be secure. There are some other problems. There's this very small group of problems, and others called discrete logarithm-based or elliptic curve cryptography. But also, these problems are hard on classical computers, and they're a founding pillar of modern-day cybersecurity. The problem is, in the quantum paradigm, and this is where I was starting to feel the heat as a grad student, factoring becomes easy. And if you would say, oh, but don't worry, there was also these other forms of cryptography, well, those become easy too. My colleague Peter Shor at AT&T Bell Labs at the time discovered it. A couple very related algorithms that broke essentially all the deployed public key cryptography methods that we rely on today. All of us. several times a day. So that's bad news. Okay? On the one hand, we want to seize all the wonderful opportunities that quantum technologies offer, but we don't want our cyber infrastructure to collapse. So we rely on these cyber technologies. Right? These give attackers, if quantum computers are available today, it would have a devastating impact on our cybersecurity infrastructure, which we rely on tremendously today. And just think about how much we relied on cyber infrastructure 10, 20 years ago versus today, versus what is it going to be like in 10, 20 years. So devastating impact if one of the foundational pillars of cybersecurity is broken and we're caught off guard and not ready with a failover plan. It's important to emphasize here that there's many ways, there's no such thing as an unhackable system. There's many ways to hack a system. Breaking the cryptography is in some sense typically the hardest way. Any security system has some physical security assumptions. It doesn't matter if you're using unbreakable crypto, if your window's open and somebody can just look in and see what your secret messages are before you encrypt them. Right? Or if there's some spyware they get on your computer. Right? Or if you have an insider who compromises you. So there's always some trust assumptions, physical security assumptions, there's implementation errors, there's all these things. When you read about all these hacks in the newspaper today, they're typically not about breaking cryptography. But we needed that. We need cryptography to be the strongest link. Because crypto is what allows us, it's the only thing that really allows us to take our information and hand it over to an untrusted entity and say, please bring that to the other side of the world for me and give it to my trusted friend. Without crypto, you can't do that. It always has to be in a secured physical box of some sort in the hands of trusted people. You can do that, but it's not very practical for something like the internet to be shuttling our bits around in briefcases with trusted couriers or some sort of equivalent. So cryptography is this wonderful thing that lets us use an untrusted infrastructure. And cryptography is the part that's susceptible to a record now, break it later attack. These other hacks of today are very ephemeral. They're very short-term window of opportunity typically. These zero-day attacks, you fix them. But crypto, you're handing it over, and for the lifetime of that information, that cryptography better not be broken. And here we're saying quantum computers would break some of the most foundational tools we use to protect our information. So that's a serious problem if we want to take advantage of what the quantum technology offers. Now what happens if we just wait a little longer, and a little longer, and a little longer? We've known about this threat since 1994. Okay? The thing is, mitigating this threat is not simple. It's very complicated. It takes a long time. In principle, we have solutions, but they're nowhere close to being ubiquitously deployed in practice. We have ideas that still need to be tested on the chalkboard and whiteboard before they're deployed in products, and standards are built around them and integrated into products, hardware and software. So if we wait until it's too late to do this changeover, then we're not just looking at a cyber punch to the face in the future, right? When you break crypto, you're breaking the foundations. There's no patch up. If an insider compromises your system, at some point you notice it, you get rid of the insider, and you can rebuild your system. If there's a security flaw in your software, you find it eventually. I mean, there's damage done, but you then fix it, and then you rebuild, and you move on. But if your crypto's broken and there's nothing to fix it, then there's nothing to rebuild with. So, I mean, and it's really important to neither underestimate nor underestimate the threat and the risk. So, maybe this is a little over the top. The flames aren't going to be quite that high, but we really are talking about a potentially catastrophic failure of our information and communication technology infrastructure if we really do nothing, do not have the failover methods at least ready to go. They don't even have to be deployed per se, but they have to be ready to go quickly when we realize this threat is coming upon us. And for many of these, you know, this could be a problem. So I've told you that quantum computers are still years away. Known about it since 1994. Relatively little has been done about it, at least in the first decade or so after that. Could we still keep waiting? Do I really need to worry about this now? I mean, the truth of the matter is, there's a lot of real, urgent, important problems in cybersecurity. Real threats hitting us, attacking us day after day after day. So we don't have a lot of spare cycles and energy and so on to be worrying about threats that aren't real or aren't going to, you know, are years and years away. We have lots of time to wait. Is this one of the threats we can put on the to-do later pile? Because we really do have a lot of important things to get done today. Well, that depends. You have to ask yourself, it's not just, is the quantum computer here today? And the answer is
wij als bij bedrijf ontwerpen, producten. Hoofdboodschap vanavond. Er zijn wat voorbeelden. Denk eens aan de graafmachine. Dus de standaard, deze standaard visie van technologie heet instrumentalisme. Technologie die ervan uitgaat dat technologie eigenlijk een soort voorzetting is van het menselijk lichaam. Alles wat wij missen, sterke handen, nou, daar is technologie dan een oplossing voor. Als we snelheid missen, we zijn niet zo snel als een luipaard. De fiets is nog steeds niet zo snel als een luipaard. Ons brein is beperkt. We kunnen niet alles vinden. Dus op die manier bij is eigenlijk geschikt voor valsen. Er zijn heel veel studies van technologische ontwikkeling eigenlijk ontstaan zijn gekomen. Heel veel studies dat er in Nederland techniek is in de 19e eeuw. 20e, 19e eeuw. Nationaal. Als je die studies beter leest, dan zie je dat het eigenlijk nog anders is. Ik neem één voorbeeld van Kodak. Meneer Eastman. Eastman. Die heeft een revolutie veroorzaakt. Waarschijnlijk dit wel uit. Heel vroeger, in ontwikkeling. Dit was zijn vinding.